Esteemed listeners, this tutorial brings to the fore the algorithm design technique called brute force strategy or brute force technique. In fact, all the tutorials which are brought to fore henceforth will only discuss the design strategies, algorithm design strategies. Okay, we will design the algorithm which are appropriate or which are apt under that particular design strategy. Then we will also analyze. So design first, analysis next. So that completes a complete circle, or that closes a complete circle. So we discuss many design strategies, okay, that are part of the curriculum of any Indian university for a UG degree or for a PG degree. Therefore, this tutorial must be useful to all the students who wish to learn the fundamentals of design of algorithms. So this tutorial brings out, as I said earlier, the brute force strategy. Okay, brute force strategy or brute force algorithm is a way of thinking or a way of solving the problem. Therefore, a way of writing the algorithm. It is a straightforward approach. The approach is directly based on the problem statement. Okay, we will go by the definition of the problem statement. With this, I mean, if we are asked to find a to the power of n, we will simply multiply a n times. So it is a into a into a into a. However difficult it is, however laborious it is, however tedious it is, we go by the definition of the problem. N times a is multiplied in order to obtain a to the power of n. Therefore, this strategy will just go with a say that just do it. Okay, some authors do refer this particular strategy as just do it policy. It does not make use of any intelligence while solving a problem. In fact, the meaning of brute is it's an unreasonable strength characterized by absence of intelligence. But anyway, some problems are addressed with brute force strategy or brute force algorithm, which vaguely mimics some of the natural or mundane day-to-day processes. Okay, those processes are also simulated, are also mimicked very vaguely, and those algorithms designed mimicking day-to-day processes in our mundane life are also coming to be designed under brute force algorithm strategy, brute force design strategy. Okay. On the other hand, there are some advantages of brute force techniques also, which cannot be overlooked. It is applicable to wide variety of problems. Okay. As a matter of fact, though it may be difficult, though it may be beating about the bush, though it may be roundabout, any problem can be attacked or any problem can be solved under brute force thinking. Okay. For some problems, brute force technique offers even reasonable algorithms even for huge input size. But anyway, a very interesting fact about this brute force design strategy is it always yields correct solution, particularly for small sized problems. Okay, it can be used to check the correctness of the algorithm designed using some other design strategy, because there are several strategies, at least 12 strategies are available in the literature. To name the few: divide and conquer strategy, decrease and conquer strategy, transform and conquer strategy, greedy strategy, dynamic programming strategy, like this. Okay, gradient search strategy, optimization strategy. Okay, there are several ways of thinking to solve a problem, and these ways of thinking are coming to be called as strategy or techniques or way of thinking or way of solving the problem. Okay, a brute is, as I told you earlier, a brute is an entity with an unimaginable, rather unreasonable capability. As a first example, we will take up bubble sort. Bubble sort is so named because it vaguely mimics rising of an air bubble raising of an air bubble contained in a water container or a water glass of water. Okay, if this is the air bubble, it rises very quickly. How? There is a physics behind this. It rises very quickly, okay, replacing every other molecule of water in this fashion, okay, which is weightier than that. Okay, it rises above, replacing or displacing or swapping the air molecules of water which are heavier than them, heavier than it, okay, heavier than the air bubble. So it rises to the top, it rises to the top vertically, okay, it comes over here. So this is a simulation of arranging things in ascending order. If you go down, or if you think this way, it is arranging things in descending order. Or if you drop a mercury bubble or bubble of mercury, it will descend down, replacing all the molecules of water which are lighter than that, and it will come and occupy the bottom position of the container. Okay, this is how bubble sort works. Okay, so every element or every bubble, the air bubble is compared with every other bubble of other molecule of water before it rises to the top. Here also every element will be compared with the rest in order to find its location, in the sorted array. Okay, we will take the example. The example is a 4-element example, 4 3 2 1. It is arranged in descending order, and we are asking the algorithm to arrange it in ascending order, because this forms the worst case input for the bubble sort. Okay, if we had we ordered this in 1 2 3 4 fashion, that is in the increasing order, the worst case scenario for this bubble sort algorithm happens to be arranging things in descending order. Okay, arranging things in descending order. Anyway, we have taken this example. We want to arrange 4 3 2 1 in ascending order using bubble sort technique. So first cycle starts, or first iteration starts. Okay, in the first iteration, the entire input will be placed for comparison. Okay, this is called as a pass. First pass has started. Okay, 4 and 3 is compared. Okay, first iteration. Within the iteration, first pass. 4 and 3 is compared. 4 and 3 are swapped. 3 comes over here, 4 goes over there. Once again, 4 and 2 will be compared. 2 will come over here, and 4 will go over there. And 4 will be here. 4 and 1 will be compared over here, and 4 occupies this place, replacing 1 over here. So what comes out of the first iteration is 3 2 1 4. Anyway, this is also partially sorted array. It needs refinement further. But anyway, what happens is, let there be any number of elements present in the array. Let it be innumerable number of elements. Anyway, the biggest of all the elements will be posted or will be placed in the last position. Okay, thus the biggest of all the elements will find its place. Okay, find its pride of place. Okay, then 3 2 1 4 will be let for the second iteration for further refining or further ordering. Okay, second iteration starts. The input for the second iteration is the output of the first iteration. Okay, 3 2 1 4. 3 and 2 will be compared. It will be 2 and 3. Swapping takes place. Then 3 and 1 will be compared. It becomes 1 and 3. Again there is a swapping, and 3 comes to this particular third position, and 3 and 4 need not be compared. Okay, and we will take a quick look at this, and we will try to avoid this comparison from happening. That means in the second iteration, if there are 4 elements, 2 comparisons will take place. Okay, the number of comparisons over here is 3, and here it is 2. Therefore, there is a reduction of 1 comparison. You can notice there is a reduction of 1 comparison. And once again, the array that comes out after the second iteration is also partially sorted. So 2 1 3 4. 2 1 3 4 is that for comparison H again, and 2 1 is compared. So it becomes 1 and 2. 1 2 3 4. This comparison is not needed, and so also this comparison is also not needed. Therefore the third iteration results in only 1 comparison. So you can notice the comparisons getting reduced as the algorithm passes iteration after iteration. So if there are 4 elements, 3 iterations are a must, and 3 passes are a must. But in every pass, there is after the first pass or after the first iteration, the number of comparisons goes on reducing one by one, reducing by one. In the first iteration it is 3 comparisons, the second iteration it is 2 comparisons, and in the third iteration it is only 1 comparison. Therefore number of iterations are n minus 1, and number of comparisons in each and every pass is n minus 1 minus I, okay, where I will generate 0 to n minus 1. Okay, with this knowledge of bubble sort, we will write the algorithm proper. Okay, algorithm bubble sort, this is the way to name the algorithm that I told you, that I have expressed this in my previous tutorial, that it should be written with camel case notation. So A 0 to n minus 1, what it does, it sorts the given list in ascending order using bubble sort. Input an array of size n not being sorted, okay, unordered, you can write like that also. Output returns a sorted array. For I equal to 0 to n minus 2, do, okay, it is less than n, it is necessary that all the n minus 1 iterations should take place. Since the numbering starts from 0, since we use the word 2, it should be n minus 2, okay, 0 to n minus 2, 0 to n minus 2. 0 to n minus 2 will also mean I equal to 0, I less than n minus 1, okay, do. For j equal to 0 to n minus 2 minus 1, minus I, actually this should be I minus I, do. So in the first iteration n minus 2 comparisons will take place. In the second iteration it is n minus 2 minus 1, because second iteration here means 1, I equal to 1, so n minus 2 minus 1, a reduction in 1 comparison. In the third cycle I will be 2, n minus 2 minus 2, reduction in 2 comparisons, reduction in 3 comparisons, like that it goes on reducing 1 by 1, comparisons will go on reducing 1 by 1, okay. So if ai is greater than aj plus 1, that is the previous element is greater than the next element, then swapping is required. Okay, if the problem is arranging things in descending order, we need to reverse it. That means if a of j is lesser than a of j plus 1, do this. Okay, that is the only change, and we should be careful enough while we answer the question whether the question is posed for arranging things in ascending order or descending order. We should be really clearly understanding this. Okay, it all depends on how do you place this. Okay, it all depends on how do you place this. If the previous element is greater than the next element, you are arranging things in ascending order. It should not be the case. Then only it requires swapping. So here only you can notice that this should be the basic step, because every element should be compared with the next element for its order, for its arrangement. If at all the arrangement is haphazard, satisfying this particular condition, the previous element being greater than the next element, then swapping is required. So at places where the array contains the elements in 2 distinct locations, okay, not satisfying this, that is if a of j is really lesser than a of j plus 1, then swapping doesn't require. Therefore it may so happen that swapping may not take place at certain locations in the array, but anyway comparison is a must. Therefore the comparison consumes most of the algorithm time. Therefore this comparison happens to be the basic step. Okay, after the happening of both the for loops, okay, the inner for loop as well as the outer for loop, what we get is really the sorted array. Then the algorithm will return this back. Okay, now we will analyze the algorithm. Okay, input size under the framework of analysis of algorithms, because it is amenable to be analyzed under the framework of analysis of algorithms, just because it's a non-recursive algorithm. Okay, so the basic operation is comparison. Okay, count of number of times. Okay, count of number of times the basic operation is getting executed as a function of input size is given by sigma. There is only one comparison. Okay, this iteration, this loop runs from j equal to 0 to n minus 2 minus I. Therefore the limits are placed over here, and this iteration is iterated, okay, from 0 to n minus 2 times. Therefore we will expand this. Okay, while we simplify, we will expand this first. So 0 to n minus 2 minus I, minus 0 plus 1. Okay, this is the expansion, and n minus 2 plus 1 becomes n minus 1 minus I, and we will separate the constant terms and the variable term, and we will apply sigma, or we will apply the summation symbol separately, and this will give us n minus 1 into n minus 1. This n minus 1 comes from the fact that, okay, n minus 2 minus 0 plus 1, okay, upon applying the limits. So n minus 1 into n minus 1, this is series. You can expand this series, I equal to 0 plus 1 plus 2 up to n minus 2. Okay, this generates a series, but the last term is n minus 2. Therefore, the summation for such a arithmetic series is, okay, n into n plus 1 by 2. Therefore, we will apply the places where n is there, we will apply n minus 2. Therefore, or we will submit n minus 2. So, n minus 2 into n minus 2 plus 1. This becomes n minus 1 divided by 2. Okay, then we will separate, we will take n minus 1 as the common factor, and what remains is, and we will take 2 as the LCM. So 2 into n minus 2 minus n plus 2. Okay, upon expanding this, upon multiplying this with a minus sign, okay, plus 2 and minus 2 will cancel away, and 2n minus n will give us n, and n minus 1 is there already, okay, divided by 2. So this becomes n into, upon simplification, this becomes n into n minus 1 by 2, or if you separate the terms, it becomes half into n square minus half into n. Okay, if you neglect the multiplicative coefficients, and if you consider only higher order term, what you get is this Cn, the complexity of bubble sort algorithm, belongs to big theta of n square, and n square complexity is also called as quadratic complexity. Okay, roughly this can be understood that if there are 10 elements, okay, 10 square comparisons would take place. Of course, this is an approximate measure, but anyway, it's a clue which will be, it is a clue as to how slow the algorithm is. Okay, it is quadratic complexity, right. And we have written, for the sake of completeness, we have written the program, C program also, only that particular logical portion. Okay, this should be helpful to you. Okay, in the selection test, etc., they will ask you the coding portion of it. Okay, nowadays they are hell bent on asking the candidates on coding. Therefore, this you need to remember this. Okay, for I equal to 0, I less than n minus 1, I plus plus. Okay, n minus 1 iterations. This will generate n minus 1 iterations. For j equal to 0, j less than n minus 1 minus I plus j plus plus. This generates passes. Okay, in every pass there is a reduction of one comparison. Okay, in the first cycle it is 0, n minus 1 comparisons, full n minus 1 comparisons do take place under the worst case. This is a very important point to be stressed. Okay, in the second iteration, I brings 1 along with it, therefore it is n minus 1 minus 1. Similarly, n minus 1 minus 2, like this. There is a successive reduction of one comparison as the iteration goes down. Okay, if a of j is greater than a of j plus 1, okay, you have to take a temporary variable, swap a of j, so a of j gets vacated. Okay, it will take a of j plus 1, a of j plus 1 gets vacated, and it will be filled with what exactly temp contain. So after the completion of these two for loops, what you get is a sorted array. Okay, sorted array, that's the thing. And you should remember here, for every comparison, if every comparison needs swapping is a very big exercise in bubble sort. Swapping is a very big exercise. Okay, it's a laborious exercise in bubble sort. And it is worth mentioning the origin of bubble sort algorithm. In an early book on programming by McCracken, Wiz H, and Lee T, published in 1959, a chapter on sorting is devoted. In this book, bubble sorting is named as exchange sort. In a book by K.A. Iverson in 1962, the exchange sorting is named as bubble sort. So we should have a feeling for this age, okay, feeling for this time. Okay, so therefore it seems probable that bubble sort may be the very first algorithm where mathematicians thought that sorting could be done, simulating vaguely the rising of a bubble in a water container. Right. Next comes selection sort. Selection sort vaguely mimics the photography photography, the group photography. Okay, how exactly this photographer takes the group photo? He will select the short people and he will keep them in the front row. Then he will select those people who are little higher than, little taller than these fellows who are being seated, and they will be arranged in other row. Okay, topping them, and once again the tallest people will be selected and they will be placed in the other row, so that his intention is everybody in the frame should be captured by the photograph, should be captured by that particular frame, should be available in that particular frame. Okay, nobody should mask the other fellow. Okay, it happens if they are not sorted. Okay, here selection happens. Okay, short to tall, shorter to tall. Okay, selection happens, then they will be sorted, so that then they will be placed in an orderly fashion. Okay, therefore this is believed to vaguely mimic the photographer's strategy he or she adopts while taking a group photograph. Okay, anyway, selection sort also has a history. However, the detail on the inventor of selection sort is not traceable in literature. However, the detailed explanation of the algorithm is found in books titled Implementing Discrete Mathematics, Combinatorics and Graph Theory with Mathematica by Skinner S. in 1990, and The Art of Programming by Nuth D., who is a prolific writer, okay, who has dealt on sorting by selection, 1998. Okay, this is relatively a recent algorithm when compared with bubble sort algorithm. It seems if we go by the time during which this selection sort technique came into fore, right? We will take an example. The strategy is, okay, we will once again take 4 3 1 2. You can recall your memory as to what kind of example we chose when we explained bubble sort. It was 4 3 2 1, 4 3 2 1. Here the array elements are haphazard in nature, and this presents worst case scenario 4 3 1 2. It is not exactly in correct descending order, but anyway it is in descending order when compared with 4 is less higher than 3, 3 is bigger than 1, 1 is smaller than 2. So this comes in a haphazard order, and this presents the worst case complexity or worst case complexity for the algorithm, or worst case input pattern, right? Now the algorithm goes like this. In the first iteration, the first element or the position of the first element is assumed to contain the biggest of all if you are arranging things in ascending order, or smallest of all if you are arranging things in descending order. I repeat, selection sort algorithm in the first iteration assumes the position of the very first element, that is 0th position, to be containing an element which is biggest of all if you are arranging things in ascending order, and smallest of all if you are arranging things in descending order. Okay, now the iteration starts, and the real smallest element will be searched within the available elements, okay, without considering this first element, because it has been assumed. Therefore the comparison goes to find the real smallest element, or the position of the real smallest element. It is rather position, not the element by value, it is a position. So here is the position where smallest element is contained. Therefore swapping takes place, only one swapping between this position and this position, 0th position and the second position. Okay, 4 will be shifted over here, 1 will be brought up over here, and 1 you should remember here, and you should feel, and you should find here 1 occupying its place in the sorted array. So it doesn't require to be a party when the second iteration takes place, because it is already placed in the sorted array. So what remains for the next iteration is only 3 4 2. So 3 4 2 comes into figure. 1 is already there in the sorted array, therefore I have drawn the partition over here. Okay, anyway, it doesn't draw any partition. Okay, it's a conceptual explanation. Okay, and let us remember this. Okay, 3 will be assumed to be the smallest of all, because you are arranging things in ascending order, smallest among the remaining elements, because one is already placed. Okay, smallest among the remaining elements. It may be wrong, the assumption may be wrong, or assumption may be right in some other input case. Anyway, the searching for the real smallest element will take place from the remaining, that is 4 and 2. 2 is found to be the smallest. Okay, 2 will be exchanged with 3, and 2 comes over here, 3 goes over there. Okay, now 2 is also admitted, 1 and 2 will be admitted in the sorted array. So 2 will find, this element will find, okay, its location in the sorted array. Okay, so what remains for the next iteration is only 2 elements, it is 4 and 3. So, okay, 1, 2, 4, 3, okay, this is already sorted. So 4 will be selected as the smallest element among the remaining. Okay, searching will take place with only 1. Okay, and this is found to be smaller than this, therefore swapping will happen. So what comes out is 1, 2, 3, 4. So therefore, if there are 4 elements, 3 iterations is a must. 3 iterations is a must. Okay, 3 iterations should happen. Okay, 3 iterations should happen, and in every iteration we will have only 3. In the first iteration we will have 3 comparisons, in the second iterations we will have 2 comparisons. Okay, to find smallest among the remaining. Okay, number of comparisons doesn't matter, but anyway there is an inner for loop, there is a separate iteration. Okay, separate repetitive comparison that should happen to find the real smallest element here in the first iteration, the real smallest element in the second iteration, real smallest element in the third iteration. Therefore 3 iterations are needed, or 3 passes needed. Okay, therefore for 4 elements, 4 iterations or 4 cycles and 3 passes. Okay, that is the thing that you should remember. Okay, it is written over here, for 4 elements 3 iterations and 3 selections, for n elements n-1 iterations and n-1 selections. Here is a selection, here is a selection, here is also a selection. Therefore the name befitting to the way in which algorithm works, therefore the name, hence the name. So we will write the algorithm. We have understood as to how this algorithm works. Algorithm selection sort 0 to n-1 sorts a list in ascending order by selection sorting. Input an array 0 to n-1 which is unsorted. This is very important. Output returns array A sorted in ascending order. Yeah, for I equal to 0 to n-2, because n-2 iterations. Since we are telling 2, we have to go up to n-2. Okay, otherwise if had it been a program, we would have written I equal to 0, I less than n-1. Less than n-1 means n-2, up to n-2. Okay, for I equal to 0 to n-2, do minimum position, because we are arranging things in ascending order. Minimum position is assumed to be the first position in the first iteration, because I is 0. Second position, that is the second position in the second iteration. Third position in the third iteration. Okay, this is an assumption, or this may be true also. Anyway, this for loop will take care to find the real minimum, the real position where minimum valued element is placed, or minimum valued element from among the remaining is available. Okay, this is very important, because for every iteration lessens an element to be a party for the next cycle, because that element will be placed in its pride of place. Okay, for j equal to I plus 1 to n-1, because in the first iteration the comparison should start from the next element. Okay, there is no need to include the element which is the position which is already assumed to be containing the minimum valued element. Okay, so the next cycle the pass will start with I plus 1 and it will go up to the last element, therefore up to n-1 do. If AR min position, okay, the assumed position, the element found in the assumed position, okay, the very first position in the first iteration, the second position in the second iteration is greater than AR of j, the next element, okay, then min position is not the assumed position. It no longer remains to be assumed position. Min position will actually become j. That means after the completion of the inner for loop, what comes out is the real min position, where the real minimum valued element is residing. Okay, then we need to swap. Okay, we need to swap that element, okay, the real minimum element, the real minimum valued element with the element that is driven out by the index I. Okay, so 0th element, AR of 0 in the first iteration, AR of 1 in the second iteration, AR of 2, so on and so forth. Okay, the minimum position will be the exact true minimum position or exact minimum position where minimum of all remaining elements is found. So after the completion of the outer for loop and inner for loop completely, or after the completion of the outer for loop, what we get is a sorted array. Therefore, the algorithm returns the sorted array. Right. Input size. Okay, we will do the analysis. Input size n. Basic operation is comparison. Okay, and there is only one comparison. Okay, comparison is this. If AR of min position is greater than AR of j, right? Yeah, 1. Now we will expand this as usual, okay, as we did in our previous example also. Okay, it is n minus 1 minus I minus 1, n minus 1 minus I minus 1 plus 1. Okay, the plus 1 minus 1 will cancel away and leaving behind n minus 1 minus I. Okay, 0 to n minus 2, n minus 1, we will separate the constant term and the variable term. Okay, I equal to 0 to n minus 2 I, and we will expand this, we will sum it out, and this is n minus 1 into n minus 1. Upon simplification, n minus 1 comes out, n minus 2 minus 0 plus 1 will give us n minus 1. So n minus 2 is out, and n minus 2, n into n plus 1 divided by 2, because this generates a series. So n minus 2 into n minus 1 divided by 2, n minus 2 into n minus 2 plus 1. Okay, that gives us n minus 1 by 2. N minus 1 is taken as a common factor. What remains here is 2 into n, 2 into 1, 2n minus 2 minus n plus 2. Okay, so once again minus 2 plus 2 will get cancelled away. 2n minus n will give us n into n minus 1 by 2, and this also belongs to quadratic complexity. But very important point here is, though there are n square comparisons, okay, the selection sort avoids unnecessary swapping that happened in bubble sort. There is only one swapping, as you have noticed in every iteration, there is only one swapping that takes place. Therefore, this is selection sort is little more efficient when compared to bubble sort. Okay, now we will question both the algorithms for against whether they possess the desirable characteristic features of a sorting algorithm. Okay, that is being in place and being stable. Okay, first of all, we will take a bubble sort. Is bubble sort in place? For this question, the emphatic answer is yes, because bubble sort will never make use of any extra array or any extra space while sorting. Therefore, it happens just like a shuffling, okay, from among the elements found in the array. Therefore, it is in place. As far as stability is concerned, we need to take an example, something like, let us say 4, 3, 2, 2, 1. Let us take this example. Okay, in the first iteration this will be swapped, and this will be 4 will come, and 4 and 2 will be swapped. Okay, 2 will go over here. Okay, and then anyway and 2 will come over here, and this 2 will move further. Okay, so the final output will be something like this: 1, 2, 2, 3, 4. Okay, this was the position of 2, okay, before sorting. That is I equal to 2, 0, 1, 2, and this position j equal to 3. Now in the sorted array, this 2, okay, this 2 which came first in the succession as an input will have its place defined in a location I dash equal to 1. and this will have J dash defined in location 2. Here also I is less than 2, and here also I dash is less than J dash. Therefore, the relative positions of equal valued elements remain same even after sorting. Therefore, bubble sort is in place, bubble sort is stable. Okay. Now we will take up selection sort. Of course, selection sort will also not make use of any extra space. Okay, it happens just like shuffling in a single array. Therefore, it is in place. Selection sort is also in place, and we will verify whether the selection sort is stable or not. We will take an example for that. Let it be 2 2 1 2 2 1. Let us say a very simple example. Okay, this is assumed to be, we are arranging things in ascending order, so this is assumed to be the smallest element among the lot, and comparison will start in order to find out the real smallest element, and it is found to be 1 over here, so 1 will go over here. Okay, 2 will come over here. So after the happening of the first iteration, the things are something like this: 1 2 and 2. Then this will be assumed as the smallest element. Comparison will take place and no exchange will take place because 2 is equal to 2. Okay, this position contains an element which is equal to an element contained in the next position. Therefore, swapping doesn't take place. But this 2 is here. Okay, so I equal to 0. Here it came over here. I dash equal to 2. And this J equal to 1, and it is here. J dash equal to 1. It so happened the earlier I was less than J, and after sorting I dash is greater than J dash. Therefore, relative positions of equal valued elements doesn't remain the same as far as selection sort is concerned. Therefore, selection sort is not stable. And we have left a few questions for our respected listeners, and they will try this because I hope that they have understood the concept of bubble sort and the concept of selection sort being brute force techniques, and they have also realized that the number of comparisons are going to be very huge in both the cases, but it comes with a difference. Selection sort does not involve itself in too much of swapping. Okay, only one swapping happens in every iteration after finding the real smallest element or real largest element in every iteration. But as far as bubble sort is concerned, there will be a huge transfer of elements, huge swapping of elements, because every non-matching of the condition will result in swapping. What is efficiency of brute force algorithm for computing a to the power of n? Okay, you write a for loop. The thing is, you have to write a for loop. Okay, you assume power equal to 1, so power equal to power into a, and for loop runs for n number of times. Okay, because n is the index or n is the exponent, so the complexity should be n, big theta of n it should be. And given a bit string 10 10 10, arrange the bits such that all zeros precede all ones. Use selection sort algorithm. Okay, you have to take it out and you have to explain each and every step. Okay, pick this as the smallest element, then search among that. Okay, this is the position of the smallest element, exchange that. Okay, something like that. You show critically, literally, how exactly comparisons happens, so that every zero will be brought to the front and everyone will follow them. Arrange the characters of selection, the word selection, in the alphabetical order by bubble sort algorithm. Okay, it's better you number them for the sake of ease, or for the sake of convenience. We will number the cardinal number of each and every alphabet. Okay, cardinal number means position value of O, position value of N, position value of S. We can do that, or we remember where we remember in such a way that SC is alphabetically should come to a greater location, alphabetically superior when compared to E, like that. You can do directly also, but anyway, the positional value of all these characters matters when we try to arrange the alphabets of selection in ascending or in alphabetically increasing order. Okay, same is the trick when you arrange the alphabets of bubble sort using selection sort technique. So with this, I think we have completed a portion of brute force algorithm design technique. Okay, the brute force algorithm design technique version 2 will also come shortly. Until then, bye.